Okay, this is a quick, helpful video for the Snell's Law PhET lab. I have both the lab and the simulation open, but I also have Chapter 17, Section 1 open as well to Snell's Law. I want to go back over how Snell's Law describes that light is changing the speed when it changes mediums that it's traveling through. Remember from back in the sound and waves unit, we talked about how waves change their speed depending on the medium that they're traveling through. We talked about how sound actually travels fastest through solids, also fast through liquids, and the slowest through the air. So sound is a different type of wave than light waves. Sound, because it's longitudinal and a mechanical wave, it requires mediums to travel. Therefore, it actually goes faster and faster as you go towards from gas towards a solid. But light, on the other hand, is an electromagnetic wave, meaning the more densely packed the particles are in a medium, the slower it's going to travel. So here we have a good example, a good picture. This green material right here is the first material that the light wave is traveling through, and you can see this blue light ray coming in towards the normal, and it goes into this brown material right here, and the red ray is the refracted light ray. Now, light can do one of three things when it meets a barrier. So right here on this boundary, the light could reflect right back into the green. It could be absorbed into this barrier right here, or it can be transmitted. Because we're talking about Snell's law, we're going to focus only on the transmitted ray, so the refracted ray. And this normal right here, this dashed line right here, is actually not real. It's fake. It's just something that we draw so that we can have something to measure the angle of incidence and the angle of refraction from. We can't measure it from the barrier because the barrier is not always perfectly flat, perfectly straight, perfectly smooth, none of that. So we do draw this normal, which is perpendicular to the surface right there where the light ray is entering into the new medium. This normal is not actually there, it's imaginary, so that's why it's a dashed line, and we always measure from the normal. So theta 1, which is the angle of incidence, or the incoming angle, is measured from the normal right there, and then we have n sub 1, which is the index of refraction of the incoming angle as well, or incoming light ray, sorry, excuse me. Then we have the second material, which is our refracted material. This one, n sub 2, the index of refraction, is actually higher than n sub 1, so we're going to see that the light ray that gets refracted, which is in red on this picture, is actually going to be a smaller angle. It's going to be tighter. It's going to bend towards the normal, and this right here is the way that the light ray would have continued going if these were the same index of refraction, but because they're different, this one is actually bending a little bit closer to the normal. So let's take a look at what this looks like on the lab. The lab tells you to go to the link right here, which I already have open. You're going to be turning on the laser, and you're going to have it on beams. So we click on our laser, boom, there it is. We wanted light ray, not wave, because then, I don't know, the waves just are a little bit harder to understand. So we're going to use the light ray. We're not going to pay attention to this reflected piece, because again, this is not important to us. We do have two indices of refraction. We have this material up here is air, this material down here is water, and I believe that's exactly what we're supposed to set up for. The medium on top should be air, the medium below should be water. Now, what we're going to be doing is we're going to be showing our work, and we're going to be measuring the refracted ray first. So if our incident ray is supposed to be 30 degrees, let's take out our protractor. We want a 30-degree angle. That means we're going to put the 0 right here on the normal. So my 0 is going to be right here on the normal, and I want my incoming angle to be 30. So I do have to move my light ray. See how that's 30 degrees from the normal right there? 30 degrees. So this is matching that my incident ray, my incoming ray, the angle should be 30. Okay? So 30 degrees. Here we go. 30 degrees to the normal. And because I don't need to move my protractor at all, I can then go ahead and measure what my refracted ray is going to be. Now, my refracted ray should be, my refracted ray should be a smaller angle because water has a higher index of refraction than air. Okay, so if we take a look here, Here's 0 again, and we're going to actually measure from 0 over this way because we're always measuring from the normal, never from the barrier itself. And this is 5, 10, 15, 20, maybe a little bit more than 20 degrees. I'll go ahead and type in 21, okay, just to be like, yeah, it's definitely not just 20 degrees, but 21 degrees is pretty close. That's my guess. That's my measured refracted ray. But now we also need to calculate that. Now, in my other video for your packet, which you may or may not have already watched, you're going to be using Snell's law. So I'm going to jump over here to my piece of paper, and we're going to take a look at this. So in my given and find table, because I always want to make sure I'm pretty organized, my angle of incidence, theta 1, was 30. Okay, I had 30 degrees. N sub 1 was 1 because that was air. You can put 1.00. I don't care if you put the zeros there or not. But this was air. That's where my light ray was coming from. It was entering water. So N sub 2, which was also given, was 1.33. We want to find what theta sub 2 is. Okay, I know I'm going to be using Snell's law. N1 sine of theta 1 is equal to N2 sine of theta 2. But here's what you may not know. When we're solving for theta 2, we have to get rid of the sine. So we're going to be doing something called the inverse sine. Okay, I'm going to show you what that looks like in just a second. First, let's plug in all the numbers we know. So N sub 1 is just 1. Wow, that was easy. Okay, times the sine of 30 degrees. And we're going to leave the equal sign right where it belongs. We're just plugging all the numbers in to where they belong. N sub 2 is 1.33. And then sine of theta 2. We can't do anything with theta 2 because that's our unknown. That's what we're solving for. So first I want to get theta 2 all by itself. Now, sine of theta 2, that's a function. I can't really break that apart yet. I have to get 1.33 to the other side. If these two numbers are multiplying, how do I get 1.33 to the other side? If you said divide, you're right. We're going to divide. It's very simple. 1.33 times the sine of theta sub 2 divided by 1.33. So that's going to cancel it. And what we do to one side, we must do to both sides. Okay? Well, let's plug this into our calculator really quick. Now, your trig functions, maybe you haven't really learned very much about trig yet, which is okay, but your trig functions are right here, and all we're using is this little button that says sine, okay? So 1 times the sine of 30 is the same thing as the sine of 30. That little number 1 isn't going to change anything. So I'm going to put sine of 30, okay, divided by 1.33, because that was my index of refraction. Sine of 30 divided by that. I'm getting a number 0.3759. I'm going to round that to 0.376. That's equal to sine of theta 2. Well, here's where we do the inverse. When we do an inverse of something, we're actually doing 1 over, or raising it to the negative 1 power. What that looks like is inverse sine. Okay, inverse sine. Where is this button? It's right above sine. So see how sine is right here? Sine to the negative 1 is the inverse. It's just the opposite of sine. It's the anti-sine. Kind of like, you know, we have a good guy and a bad guy. The good guy is sine, and then the anti-good guy is the bad guy, and that's anti-sine or inverse sine. Okay, so what we're going to do is inverse sine of theta 2, that's just going to give us theta 2. And we're going to plug this into the calculator right here, inverse sine of this number. So I'm going to do shift sine, and I'm going to do 0.376, I think is what I rounded it to, 0.376 equals, and look at that, theta sub 2 is about 22.1 degrees. Man, that's really close, really close to what I had as my answer. Let's take a look. My measured refracted ray was 21, but I calculated it and it was 22.1, and that's super close right there. So that's how we're going to solve for theta 2. But that's not the only thing we're going to calculate. We're going to go one more step, and we're going to calculate the speed of light in the material. All right, the speed of light in the material, let me go back to chapter 17, comes from this equation right here. This one from your homework. The speed of light in a vacuum is c, 3 times 10 to the 8th meters per second. If we divide that by the index of refraction of whatever the material happens to be, we're going to get the speed of light in that material. We put this on our equations sheet on our packet, and so I'm going to go ahead and just skip forward, and let's calculate the speed of light in water. Guess what? It's always going to be the same, which is pretty cool. So there's nothing really new here. We're going to go ahead and just use this equation. V is equal to C over N, and we're going to plug in what we know. We know the speed of light in a vacuum is 3 times 10 to the 8th meters per second. We wrote that last week or the week before. It's on our packet. This is the speed of light in a vacuum. This is what we're always going to use, okay, for letter C. And then we're going to divide it by N. This one is for water, and our N for water, which was N sub 2, is 1.33. So when I plug this into the calculator, let me go ahead and clear everything from the last problem, okay? When I plug this into the calculator, 3 shift log, remember we're doing the times 10 button, which is that shift log, the 10x to the 8th power, and we're going to divide that by 1.33. And we don't have to use any parentheses because everything is going to be typed in correctly the way that we want it to be. This is a really big number, so we're going to write 225, comma, 563, comma, 909.8, or we could just do 910 if I round it up, okay? Meters per second. Now, you can write this on your lab, that's perfectly fine, or you can simplify it using scientific notation. Scientific notation, I would be putting the decimal right here. I would be rounding, so I would say 2.26, since this is a 5 right there, times 10 to the 1, 2, 3, 4, 5, 6, 7, oh wait, 8, yeah, okay, sorry, 1, 2, 3, 4, 5, 6, 7, 8, okay, I just wanted to double check because I did that a little too fast. Both of these are correct answers. You can type either of them in. Either of them works for your answer for number 1. So again, if I typed in 225, 563, 910 meters per second, that is still the correct answer. We could even put our commas in there and make it look nice and neat. Still the correct answer for the calculated speed of light in that material. And again, that's for water. Now, as you continue the lab, you're going to be doing the same things, except for you're going to be changing the indexes of refraction, okay? The different incident rays are going to have different refracted rays, and then we're still going to be calculating them. You're going to keep the same materials for this, but then down below, you'll start to change some other things, okay? We're going to go from water into glass, and you're going to see some stuff that's going to change. For part 3, you're going to be looking for mystery materials, which is pretty cool. Don't forget to insert an image of your calculations right there. If you have extra questions on the packet, or I'm sorry, on the lab, and you would like to see more stuff done, please don't hesitate to ask Ms. Davis for some help, and she will let me know, and I can make another video.